In this video, we're going to talk about continuous random variables. Now, unlike discrete variables that have a countable number of possible values, a continuous random variable has an uncountably infinite number of possible values that it can take on, which means that if we were looking for the probability that x equals any one of its values, little x, that would have to be 0, because there's just too many values for that to have a positive probability. So we can't use a probability function. Instead, we define a probability density function as follows. We call it little f of x, and we define it such that the probability that x is between a and b, two values, is the integral from a to b of little f of x dx. By definition, that's also equal to the probability of x being less than or equal to b minus being less than or equal to a, so big F of b minus big F of a. And then by the fundamental theorem of calculus, that means that little f of x is just big F prime of x. I'll draw a diagram to show you what I mean. Say we want the probability that x is between a and b. That would be the area underneath the little f of x curve, this shaded region here. But we could also get that by taking the probability of being less than or equal to b minus less than or equal to a. That would be big F of b minus big F of a, or that integral from a to b of little f of x dx. Little f satisfies some properties, including that the integral from negative infinity to infinity must be 1. So the area under the little f of x curve has to be 1. That's because the variable has to take on some value somewhere within the real line. So we have to have a probability of 1 of taking any possible value. Also, little f of x is going to be non-negative, but it can be bigger than 1. And that means that little f of x is actually not a probability. That seems kind of weird. We're used to thinking of little f of x being a probability, but it's actually not because it can be bigger than 1. Instead, it has a slightly different interpretation. Let's say we have a curve here, little f of x, and we have a value x and x plus epsilon, so some very small interval of length epsilon. And if we wanted the probability that the variable x was between little x and little x plus epsilon, we would want this probability here. Now, officially, that would be the integral between those two values, but a really good approximation would be the area of that rectangle. So the width of that rectangle is epsilon, and the height of that rectangle is little f of x. So essentially, little f of x is like a multiplier for the interval length that tells us the approximate probability of being near the value little x. So it's not a probability, but if we multiply it by a small interval length, it gives us a good approximation of the probability of being in that region. And the smaller the interval length, the better the approximation. Even though little f of x is not actually a probability itself, it plays a similar role. If we wanted the expected value or the variance of a continuous random variable, we would just take the integral of x f of x dx, or in the case of the variance, x squared f of x dx, and then subtract the mean squared. And again, we're taking that integral over the entire real line, but little f of x might be 0 for large portions of that real line. So when we integrate from negative infinity to infinity, often we just end up integrating from the lowest value in the range to the highest value in the range. I want to talk about 4 different discrete or continuous random variables in this class. The first one is the simplest. We have a uniform random variable, and it's characterized by a constant probability density function over the region from a to b. Otherwise, it's 0. So to graph this, it would look something like this. There's A, there's B, and it would be straight at 0, and then straight, and then straight. So 3 straight lines. Notice that we do have 2 discontinuities there at A and B, and that's okay. And the height of that top line there is 1 over B minus A, which means that the area underneath that curve, it's a very boxy curve, the area of that rectangle is 1, because it goes from A to B on the bottom, and from 0 to 1 over B minus A on the top. For that same random variable, we can easily find a closed form expression for the cumulative distribution function by integrating from the bottom of the range up to x of the probability density function du, and that's by the fundamental theorem of calculus. So we'll do this integration, relatively straightforward, and that gets us x minus a over b minus a. But that's only true if x is between a and b. We need to care about those other cases too. So we have x minus a over b minus a for x between a and b, 0 if x is less than or equal to a, and 1 if x is greater than or equal to b. And we can graph that as well. We see that we have 0 up to a, a straight line going up to b there, and that is at 1. And the slope of that line is 1 over b minus a. We can find the expected value of this uniform random variable by integrating x times f of x dx over the entire range. Doing that integration gives b squared minus a squared over 2b minus a, and then we can factor the top to get this, and the b minus a cancels out. So we end up with a plus b over 2. And I want you to think about why that makes sense. If we have a uniform random variable, it looks like the average value, which is what the expected value represents, is exactly halfway between the endpoints, which makes sense, right? On average, if it's completely uniform, the value will be halfway in between the endpoints. Similarly, we can find the variance is equal to b minus a quantity squared over 12. And I want you to give this a try, especially if you're a little bit rusty with your integration. Try integrating x squared f of x dx over the integral from a to b. And remember that our f of x here is just 1 over b minus a. So integrate that, see what you get, and make sure that you can show that that variance equals b minus a squared over 12. It should make some logical sense that the variance is proportional to the range of the random variable squared, because variance is a measure of the average squared distance from the mean. All right, that's everything about the uniform random variable. Next, I want to talk about the exponential random variable. This is very closely related to the Poisson process because we're going to let x be the waiting time until the next event in a Poisson process with rate lambda. So the parameter is that value lambda. We're going to start by finding the cumulative distribution function and then integrate it. So if we want the probability x is less than or equal to x, that's just the probability that the time to the next event is less than or equal to x. And for that to happen, we need at least one event to occur by time x. So if here's a timeline, we want our first event to be somewhere in that first region. So if we define y to be the number of events in that time period from 0 to x, we just want the probability y is greater than or equal to 1. And y is Poisson, and so that gives us the following. We end up with 1 minus e to the negative lambda x, as long as x is greater than 0 and 0 otherwise. So then we can find the probability density function by taking the derivative of big F of x. And using the chain rule, that gives us lambda e to the negative lambda x. So let's graph these functions. Our big F looks like this. It's kind of asymptotically approaching 1 as x goes to infinity. And there's a point of non-differentiability at 0. And the probability density function looks like that. So there's a jump at 0 from 0 up to the value lambda, and then it asymptotically approaches 0. Now, the exponential distribution has a really neat property known as the memoryless property. So imagine we have a timeline here, and suppose we know that by time x, no events have occurred yet. And what we want to know is, what does that tell us about whether or not any events will occur by time x plus y? So what can we say about that, knowing that we've already waited x units of time? What we're asking for really is the probability x is greater than x plus y, given x is greater than x. And subbing in the definition of conditional probability, that gives us the probability that x is greater than x plus y and greater than x, divided by the probability x is greater than x. For the top then, we can see that that just simplifies to the probability x is greater than x plus y, because if it's greater than x plus y, it's automatically greater than x, assuming x and y are both positive here. So we don't need that second condition, it's automatically satisfied. But then the denominator stays the same. So now we can use what we know about our exponential random variable. This is just, 1 minus the CDF of x plus y over 1 minus the CDF of x. And then we can sub in, and we'll get this expression here. Some beautiful canceling happens. The 1 minuses cancel out, and the e to the negative lambda x cancels out, and we're left with e to the negative lambda y, which is just the same thing as the probability x is greater than y. So look at what we have here. We've shown that the probability that we have to wait at least x plus y units of time for the first event, given that we've already waited x units, is the same as the unconditional probability that x is greater than y. So essentially, all of the waiting that we've done by time x has no impact. It has no effect on how likely it is for us to get our next event. It has no effect on the distribution of the future waiting time. So all of that weighting was for nothing. That's why it's called the memoryless property. It has no memory. If we wanted to find the expected value of x, or the variance, we would need to do some pretty ugly integration. X and then an exponential of x, it's a bit of a mess. And to do that, we might need to use integration by parts, which is no fun. Or there's another trick that you can do to avoid that, known as the gamma function. So the gamma function is defined as follows. Gamma of alpha is the integral from 0 to infinity of x to the alpha minus 1 e to the negative x dx. And if alpha happens to be a natural number, it's equal to alpha minus 1 factorial. You can actually prove that using integration by parts if you really want to, but I won't make you do that. So we have this function, it's an integral, but it also equals alpha minus 1 factorial if alpha is a natural number. So we can use that because if we can manipulate an integral to look like a gamma function, then we don't have to do the integration at all. We can just say, ha, that's gamma of alpha, so that's just alpha minus 1 factorial. So let's see how it works. If we want the expected value of x, it's going to be equal to the integral from 0 to infinity of x times f of x dx. And again, for this exponential random variable, that's x lambda e to the negative lambda x dx. So we're going to do a substitution. We want to manipulate this integral so it looks like a gamma function. We'll let y equals lambda x, and that means x is y over lambda and dx is dy over lambda. And we can sub that in, and our integral will look like this. So it's the integral from 0 to infinity of y over lambda, lambda, e to the negative y, 1 over lambda dy. One of each of those lambdas will cancel out, and we'll be left with the following. 1 over lambda times the integral from 0 to infinity of y to the 1, which we could write as y to the 2 minus 1, e to the negative y dy. And we can recognize that whole integral is just gamma of 2. But gamma of 2 is 1, and so we end up with the mean of 1 over lambda. Now, I want you to think about why that makes sense. If lambda is the rate of our Poisson process, then this is telling us that the average waiting time until the first event is 1 over lambda. Why does that make sense? Pause and think about it. Well, it should make sense because the more frequently events are occurring, in other words, the higher lambda is, the less time we would spend on average waiting for an event to occur. And the opposite would be true. So it should make sense that those two things are inversely proportional to each other. We can do the same thing for the variance. We need to find e of x squared, which is, again, the integral of x squared f of x dx. And again, we'll just manipulate that integral using the exact same substitution to try to get it to look like a gamma function. So now we have y squared over lambda squared, lambda e to the negative y, and then 1 over lambda dy. So again, one of the lambdas on the top and bottom will cancel out, and we'll be left with the integral of y to the 3 minus 1 e to the negative y dy, which is gamma of 3, and that gives us 2 over lambda squared. So finally, the variance gives us 1 over lambda squared. Third distribution for today is the gamma distribution. So imagine x is a gamma distribution. We're going to define it with the following probability density function. It's x to the alpha minus 1, e to the negative x lambda, lambda to the alpha over gamma of alpha. So it gives us a distribution you might not have seen before in Stat 230, but essentially it's kind of like a generalized version of the exponential. And it's defined for x greater than 0. It's 0 otherwise. So we can actually check whether or not this is a valid probability function, check that it's equal to 1. We'll pull out everything that doesn't depend on x, and then we get a function that looks like this. And then we'll do the same trick as before. We'll try to manipulate that integral to look like a gamma function. So we'll do that same substitution that we did before, y over lambda subbing in for x, and y subbing in for lambda times x, and we'll end up with the following. Those are our constants out in front, and then we'll have 1 over lambda to the alpha, and then our integral from 0 to infinity of y to the alpha minus 1, e to the negative y, dy. If you're not sure where all the alphas and things have gone, notice that there's alpha minus 1 powers of lambda on the bottom in the integral, and then an extra one right beside the dy. So all of those together, we pull them outside, and that gives us our lambda to the alpha in the denominator. But then that integral that we have there that's left is by definition gamma of alpha. So that whole thing gives us 1. So that means that no matter what the value of alpha is, and no matter what the value of lambda is, this is a valid probability density function. We can actually find the mean is alpha over lambda, and the variance is alpha over lambda squared. And if you want to practice working with gamma functions and doing these integrations, I highly recommend it. Again, you're not going to be doing a ton of that in this course, but it's good to be able to understand how those work. And you don't need to use integration by parts at all if you master this trick of manipulating integrals using those gamma functions. So give that a try if you like. There's also a cool interpretation of the gamma random variable. If alpha happens to be a natural number, we can actually imagine a gamma random variable as the total waiting time until we see alpha events in a Poisson process with rate lambda. So it's kind of similar to an exponential, but we're looking at more possible events occurring. So here's a timeline, right? There's the first event, the waiting time until that is exponential. There's the next event, the in-between waiting time is exponential, and that third event took a while. Or we could just look at the total waiting time for all three events to occur, and that gives us our gamma with parameters 3 and lambda. So what that means is two things. First of all, if we have alpha equals 1, then it's just an exponential. And you can double check that too if you plug in alpha equals 1 to the formula. And also, if we have a whole bunch of independent exponentials and we add them up, the result is a gamma random variable. So that gives us this neat relationship. So here I have a little summary of all of the variables that we've talked about so far. There's two different processes we've talked about, Bernoulli trials and the Poisson process, which are fairly similar to each other, just Bernoulli trials are in discrete time and a Poisson process is over continuous time. And then for each of those, there's a few different random variables that can come up. So firstly, if we're thinking about one trial of an experiment, then we have a Bernoulli random variable with parameter p. And there's no such thing as a single trial in a Poisson process, so there's no matching variable there. So if you have just, something that can either happen or not, you know that you want to use a Bernoulli random variable and that the probability of the thing happening is p, and that's your only parameter that you need. We also have the idea of a counting random variable. And that's something where you're counting up the number of events or the number of successes over a known amount of time. If we're doing that for the Bernoulli trials process, we end up with a binomial. And if we're doing it for a Poisson process, we end up with a Poisson. So again, there's something very similar between these two variables. They're both counting up the number of events or the number of successes over a fixed amount of time or trials, and they end up with these two distributions. So the binomial has two parameters, n and p. The Poisson has a single parameter, which is lambda times t, but both of those are counting random variables. Next, we have the idea of the waiting time random variable. So if we're waiting for an event to occur, that would be a geometric in Bernoulli trials, because the geometric is how many trials it takes to get that first success. But if we're doing a Poisson process, the waiting random variable is an amount of time, not an amount of trials. So that's the exponential distribution. So even though both of these variables are waiting random variables, geometric is discrete because we're counting up the number of trials, whereas exponential is continuous because we're measuring an amount of time. And the key similarity is that they're both waiting for something to occur for the first time, whether it's a success or it's an event. And then lastly, we have kind of the generalized version of those. If we're waiting for multiple events in Bernoulli trials, we end up with a negative binomial random variable with parameters r and p. If we're waiting for multiple events in a Poisson process, as I just described, you're looking for a gamma random variable with parameters alpha and lambda. So this is kind of a really neat summary of all of the distributions so far, I guess except for the uniform, that doesn't fit on this chart, but all of them relate to one of these two processes, Bernoulli trials or the Poisson process, and they can be categorized as, counting random variables or weighting random variables, and this is how they fit together. There's also a few relationships that we've seen that I want to highlight. So first of all, we know that the Bernoulli is a special case of a binomial, the geometric is a special case of a negative binomial, and the exponential is a special case of a gamma. So all three of those have this relationship where if we set one of the parameters in the multi-parameter distribution to 1, we just get the other type of distribution. So that's kind of neat. That relationship holds for all three of those pairs of distributions. And similarly, we can go in the opposite direction. If we take a sum of Bernoullis, we'll get a binomial. If we take a sum of geometrics, we'll get a negative binomial. And if we take a sum of exponentials, we'll get a gamma. So all of those work in that same way as well. They have to be independent for this to be true, but we're basically either waiting for multiple events or counting up numbers of events on multiple trials or multiple periods of time. And that gives us this relationship. The Poisson looks kind of lonely there, but actually it has its own kind of relationship. If you take a sum of Poissons that are independent, you get a Poisson. So it gets an arrow to itself because you can get a Poisson by adding up other Poissons. Finally, I wanted to note that we mentioned the memoryless property of the exponential, but the geometric also has that same memoryless property. It's not quite as general, it only works for integer values of x and y, but you could actually go back and prove that the geometric has this memoryless property as well. And that makes sense, again, because Bernoulli trials and Poisson process don't remember what happened in the past. So if you're just waiting for a success or waiting for an event to occur, it can't matter how long you've already been waiting. All right, that's a nice little summary, and hopefully this is helpful if you're a little bit rusty on determining when to use which distribution. So think about what you're being asked for. Is it Bernoulli trials or is it a Poisson process? And are you being asked to count up the number of successes or events in a certain period of time, or wait for a certain number of successes or events? Print this chart out and you can have it with you every time you take a test. Finally, the very last distribution that I want to talk about today is the good old normal random variable. So we say x is normal with parameters mu and sigma squared, or actually sometimes people say Gaussian instead of normal, if the probability density function looks like this. So it's a pretty messy looking function, 1 over root 2 pi sigma, and then e to the negative 1/2 x minus mu over sigma quantity squared. And it's defined for all real values of x. It looks like that nice bell curve that everyone is familiar with. So a few properties of this normal PDF. Obviously it's symmetric about mu, and the maximum occurs at mu, and both the tails drop off fairly quickly, exponentially to 0. We can't actually integrate this function analytically, which means we need to use tables to evaluate a big F of x at any point. And also, we have these parameters, mu and sigma squared, are defined as the mean and variance. That's why they're named that. We do have also a special case, which is the normal 0, 1, and we sometimes call that the standard normal, and often use z instead of x to refer to it. That's what happens when we sub those parameters in. We just get a really nice looking function, 1 over root 2 pi, e to the negative 1/2 x squared. And sometimes we give that function a name, little phi of x. So that's the lowercase Greek letter phi. It's still not integrable though. It looks pretty nice, but it still can't be integrated. So if we want the big F of x here, we just integrate phi of u du from negative infinity to x, and we have to use some kind of numerical integration technique or a table to get that. But what we get, we call capital phi of x, and that's the standard normal CDF. This is useful because if we have a general normal random variable with any mean and variance, then we can do a simple linear transformation. We can take x, subtract its mean, and divide the whole thing by the standard deviation. That will be a normal 0, 1. Which means that any normal random variable that we're working with, we can transform it to a normal 0, 1, and then we can look up anything we want, any probability or any percentile that we're interested in the normal 0, 1 tables. All right, that is everything for continuous random variables. There's one more video this week about transformations and moment generating functions, so watch that, and then I'll see you at tutorial.